So this video will be about two things. These things called vectors and then something called free body diagrams. So this starts our unit on forces. And forces are a really big deal in physics. Okay, forces, as we're going to see, are things that change the motion of an object. And in order to study forces, we have to also study them as these things called vectors. So before we get to forces, let's talk about what vectors are. So in physics, you'll run across several quantities, and we'll talk about those in the next slide, that have a special property in that there's an amount, which we call a magnitude, and then there's also a direction that you have to specify. Okay, so one of the big ones that we've studied already is displacement. So it's one thing to say that I've moved maybe 15 meters, okay, but that would be a distance, but for displacement I need to say, oh, I moved 15 meters in that direction. And what we do is we use an arrow to represent the direction. So when you see a vector quantity, a lot of times you'll see it represented with an arrow. Okay, so this would be a vector. Okay, and this, we could say that this is the displacement. And so a lot of times for vectors, we'll put like a little arrow above it when we're talking about vectors. And then there's something else called a scalar. And I just want you guys to be familiar with this term. Okay, a scalar only has magnitude. Okay, so a scalar doesn't have a direction. So a good scalar would be mass. If I had a mass, I'd say, oh, that thing has a mass of 10 kilograms. I don't need to say, oh, it's 10 kilograms to the north or to the west or whatever. That makes no sense. So mass is a scalar quantity, and we only have to tell the amount of it. Whereas things like displacement are vector quantities, where to really tell what the displacement is, you have to tell me both the distance, the magnitude of it, and the direction that displacement's in. Okay. Now, as we go on, when we have a lot of vectors or a lot of vector quantities in the same place at the same time, we'll have to add them together or subtract them in certain ways. So for right now, to add vectors together, if they're pointing in the same line, okay, so we're going to limit our study right now to just vectors that point along the same line. So if they're in the same line, and say I move 5 meters that way, and I move maybe 10 meters this way, I will add these two together. So if I add vectors together and they're pointing in the same direction, then I would say that the result, which is we call the resultant, will be 15 meters. Okay, go in that direction. Notice the size of the arrow. I should probably make this a little bit smaller. The size of the arrow indicates the magnitude in a vector. Okay, so theoretically, if I would have drawn this to scale, I could take the length of this arrow plus the length of this arrow, and that should be the length of this following arrow right here. Okay, if I have a vector though that goes 5 meters that way, and then I have one pointing the opposite direction, that's 10 meters, even though I don't have a negative sign, you can kind of see if I add these two together, if they're pointing in opposite directions, I need to subtract the magnitude. In fact, this one would be 5 meters going to the left. Okay, very often, we kind of use the cardinal direction, so we'll say this is north and that's south, this is east and that's west, and so we would say it's 5 meters to the west. Okay, so if they're pointing in the same direction, when we add them together, you add the magnitudes together. If vectors point in the opposite directions and you add them together, you need to subtract those two magnitudes. Okay, so just kind of keep that in mind as we go forward. So as I said, there's lots of vector quantities in physics. For right now, here's the ones that I want you to know about. We already talked about displacement. Okay, so displacement is a vector quantity. Okay, I could say 5 meters, let's make that 15 meters, kind of going up and to the right. Velocity is also a vector quantity. We've seen this in our motion diagrams, right? So I could have like a 10 meters per second pointing up. Okay, that's my velocity. And acceleration is yet another vector quantity. We saw this with our kinematic equations problems when we were doing our motion diagrams. We had acceleration pointing in a certain direction, so maybe 3 meters per second squared going to the left in this case. Okay, and as we'll soon see, force, this is why we're looking at vectors now, force is another vector quantity. Okay, and so to specify a force, you need to tell both how big the force is and the direction that the force is applying or being applied in. So very simply, a force, we can say it's a push or pull. Okay, so forces are pushes or pulls. They can be caused by physical contact. So sometimes you will, physically, like you can touch something, you can push or pull it, or maybe a string or a chain is attached to something and it's being pushed or pulled. Okay. These are called contact forces. And then, and these, we experience this all the time, but they can be caused by fields. Okay. For example, in this case, gravity. Gravity is a field force. So we feel a force of gravity, and we would feel a force of gravity even in space due to the Earth. If we're kind of in space above the Earth, we would still feel that force of gravity even though there's no contact between us and the Earth. And so these are called field forces. Okay. Now, the unit of force is what's called the Newton, and it is named after Sir Isaac Newton. We abbreviate with an N. Okay. And it is also a vector. So I could say that if I say I push something this way, I can apply 10 newtons of force to it. Okay. Now the newton is made up of other things. It's a kilogram times a meter over second squared, and we'll see why that is later. Okay. But we rarely do we write kilogram meter per second squared. Usually we'll just write newton. Okay. So we have these forces and we want to study them, and we want to see how we want to find out how is it going to change the motion of this object. In order to do that, we need to identify all the forces acting on an object, and that is where free body diagrams come in. Okay, so just a kind of a simple example here, a free body diagram. Let's say that I have, maybe I have a book. Okay, so I have my book. And maybe, I have my hand here. Can't draw a very good hand. So I have my hand here. Okay. And, wow, that's a really thin wrist. Let's try this again. So I have my hand here. Okay. And I'm going to just hold this book in the air. Okay. And I want to represent all the forces acting on this book. Okay, so this is, book being held in air. Being held in air. Now, the free body diagram for this, we're physicists, we're not artists, as you can tell from my picture here. And so instead of drawing the hand in the book and all that, what we'll do is we'll draw a dot. Okay, and this dot is going to represent the book. And then I'm going to use vector arrows to represent the forces that are acting on this book. So I look at this, and remember I have two types of forces. I have a contact force and I have a field force. So when I do a free body diagram, I ask myself two questions. What is in contact with the object? Okay. What is in contact and applying a force? This is question one. Question two, what fields are producing forces? These are the two questions that you should always ask when you are thinking about a free body diagram. And so my first question, what's in contact and applying a force? Well, in this case, it would be my hand. Okay, my hand is applying a force to this book, and it's going to apply a force going up. So I'm going to draw a vector. I'm going to draw this arrow, and I'm going to say that this is the force of my hand. Okay. Now, if that was all that existed, I mean, that's all I can see, right? And if I'm thinking of the forces in the book, it would just be the force hand. But if that was the case, then the book should be accelerating upwards. Okay, and it's not. It's just being held in the air. So there's got to be some other force acting on it. And so this is my second question. What fields are producing forces? Well, this book has mass, and gravity, if something has mass, it's going to feel a force due to gravity. And so although I don't see it, there is a force of gravity acting on the book. And so I'll say F sub G for that. And this is my free body diagram. Okay, so the free body diagram indicates the object with a little dot, and then I'll draw all the force vectors on it in the direction of the forces. And to the best of your ability, you want the length of the arrow to represent how big the force is. So the book is being held in the air. The force of the hand and the force of gravity should be the same in this case, and so I'm going to draw them the same length. So we're going to practice this a lot in class, guys, how to draw these free body diagrams, because it's very important that you know how to do this before we move on and study the effects that forces have on the motion of an object. So I hope this makes sense to you. If you have any questions, please let me know.